Now, okay. Now today we're going to talk about the universe itself and why redshift has given us evidence of an expanding universe. Okay. Now, there are two notable things that I want to share with you. Number one is that redshift shows the evidence, because we never see blue shift, it's always redshift. So redshift shows the evidence of basically expanding universe. So by observation of many galaxies, we have learned that the faster the galaxy is moving away from us, the more red shifted the light from it is observed. Right? Now, so what you guys need to understand is it's just like an analogy of a balloon. Which basically shows that if a person is blowing a balloon like this, and the balloon has 4 dots right here, so when the balloon basically expands, like becomes bigger, so the expansion is happening in each direction. So basically all the dots also move away from each other like this. So that's just an analogy how the galaxies, the balloon itself is the space where the galaxies exist, and then if you keep them expanding, so they will move away from each other, and that's what we're witnessing from the fact that every galaxy is being redshifted. All right, is that clear, everyone? Hello Ramin and Abdul Mois, how are you? And Nadia, how are you?
Great, sir.
Okay, yes. Okay, you guys have written it. Anything you would like to ask? Now, one of the most important scientists ever existed was Edwin Hubble. Okay, and there's a Hubble telescope as well. You should read about it if you're interested in this. But basically, so right now we are going to do Hubble's, right there, the heading Hubble's law and the Big Bang theory. Now, Edwin Hubble basically investigated many galaxies, a very large number of galaxies. So, Edwin Hubble basically observed many galaxies using the data gathered by the redshift and standard candles methodology. Okay, now redshift basically enabled him to find velocity of recession, which basically means how fast they're moving away from us, and the standard candle method enabled him to find the distances from Earth, like that, right? Now, the Hubble law can come for 2 marks. What you need to remember is the recession speed, in fact, of galaxies moving away from Earth is proportional to their distance from the Earth, like that. Okay, so this is the definition that you should remember. So what he says is that the velocity of recession is proportional to the distance from Earth, like we said. Oh my god. मेरी गाड़ी मैकेनिक के पास है। अच्छा। उसको कहें जो काली गाड़ी खड़ी है नीचे वो आप दो। कौन सी रोज वाली गाड़ी? काली गाड़ी अंदर खड़ी हुई है। अच्छा, तो उसकी चाबी किधर है? ये इनसे लें, ये अबू बकर से। अच्छा ठीक है, उसको दो ना। हाँ हाँ ठीक है। Okay, now so when you remove the proportionality sign, what you get is the Hubble's constant, h naught times t. All right, this is let me put it, velocity of recession Hubble constant, and this is the distance between galaxy and Earth. Alright, so this you should remember. Now, Hubble's constant. Oh, by the way, let me just show you. This is second minus 1. This is the same as meters per second, don't remember. And that's the meter because it's distance, so don't worry about that at all. Now, so how he has done it, that basically he has found this constant by plotting all the galaxies he observed on a graph where one side had the velocity of recession and the other side had the distance, right? Uh-oh. So basically the galaxies appeared to be clustered like this, right? So he has put like a data of so many galaxies actually. And from this, he drew a line of best fit like this. So the galaxies are clustered around this, right? So what he basically says is that if you find the gradient of this line, rise over run, so the gradient basically represents the Hubble constant. And you can actually see from the graph itself, suppose this galaxy we're talking about. So the galaxy which is the most, which has the highest speed is also the one with the greatest distance, okay? So we can say that this is basically more distant galaxies are moving away at a faster velocity, all right, and vice versa, that the ones which are nearer, like you can see here, near Earth, they have smaller speeds. Is that clear? Aman, Hassan, Atik?
Yes, sir.
Okay. Ramin, everything is clear? Suman? Gatika? Nadia?
Yes, sir.
Very good. Now, thanks to Mr. Hubble, it has enabled us to estimate the age of universe. Okay, so you can draw this first and then we can move forward. It's very simple, nothing biggie really. All right. Now, just for your own knowledge, Hubble constant keeps on changing as we discover more galaxies every day and year. So it's not a fixed value though, but it has helped us trace the the time, right? So when the universe began, right? So put the next heading, the age of universe. So how it is estimated really? So basically we can say that if the galaxies are moving away from each other, that means they must have started from some point, or same point, let's write same point, at some time in the past, right? Now, if it is considered to be true, the universe likely began in an extremely hot and dense singular point. Which subsequently began to expand very quickly. So basically, this idea is known as the Big Bang theory. All right? So, if we extrapolate, Hubble's law back to the point where it is believed universe started its expansion right? The age of universe can be found using T naught equals to 1 upon H naught. So this is basically the age of universe, and this is the Hubble's constant, right? Now, so now let's do a question to estimate the Hubble's constant, okay? Sorry, the age of the universe. So now the question suggests that a galaxy is found to be moving away with a speed of 2.1 times 10 raised to power 7 meters per second. The galaxy is at a distance of 9.5 times 10 raised to power 24 meters from Earth. Assuming the speed remains constant What is the age of the universe? Now, these sort of questions, the first thing you're going to do is you're going to find the current Hubble's constant. So you're going to do V is equal to H naught over D. Now, H naught will be equal to the speed, which is 2.1 times 10 raised to power 7 divided by the distance, which is 9.5 times 10 raised to power 4. So we get 2.2 times 10 raised to a minus 18 second minus 1. A lot of time Hubble constant will be given as picoseconds. So you need to remember, they might write it as P minus S. Do not worry, that means picoseconds. Alright, anyway. Now, the age then can be determined by the age of universe is 1 upon the Hubble constant, whatever it is. So 1 over 2.2 times 10 raised to minus 18, and that would be 4.52 times 10 raised to power 17 seconds.
Sir,
Yes.
can we just divide D by V?
Yeah. Yes, you can do that. That's a faster way. I'm just, explaining it once, like that. Anyway, now you got to change this into years. So to convert it into years, you need to divide it by 365 days, 24 hours, 60 minutes, and 60 seconds. This should give you 1.43 times 10 raised to 10 years, which is equivalent to basically 14.3 billion years ago. We can estimate the universe basically was created by a Big Bang. Is that clear, everyone? So now, like I said, why it's a theory? Because the Hubble constant is not exactly a constant. It's not exactly how we see it, but it keeps on changing. That's why our estimates are changed from now and then. So I don't know, currently the Hubble's constant, Hubble constant value today. So you have to basically find it every now and then. Right now it is about, in 42. It's basically about this much, 73 kilometer per second megaparsec. But megaparsec, basically parsec is a unit, astronomical unit that we don't use anymore. So in second minus 1. Okay, wait. So in 1 mega, we have to find it through parsec right now. Unfortunately, we don't have that. Okay, it's right. It's if it was 76 many years ago, it's 2.2 times 10 raised to power minus 18 seconds. But from 76 now it has converted like 70, so it keeps on changing a bit. The thing is that's why we can but safely say it's around 14 or 13 billion years ago that the universe was created. All right, now congratulations, you have finally completed your A2